Hi guys, it's Mrs. Allison. Today we are going to talk about a concept called linearization that I think is probably review for most of you. But to get us started, let's look at the warm-up, a fun little optimization problem. So hit pause, take a second, and try the warm-up problem. All right, hopefully you noticed it is an optimization problem. We know that it is going to be, mostly because of that phrase, we want to find the maximum of something. So this maximum slope, weird, that's not the color I chose, maximum slope is what we're trying to maximize. Okay, so we're trying to maximize slope. So I need an equation for slope. Well, what is that? So if I'm trying to maximize slope, the first thing I need to do is write the equation for the maximum. And the equation for the maximum slope would be the first derivative. So f prime of x equals negative 2 minus 2x minus x squared. But here's the tricky part. If I want to find a maximum slope, I need to actually take the derivative of the slope function, because all this is the slope function. So to maximize this, we need to take the derivative of this slope function, which just happens to be the second derivative. So we get negative 2 minus 2x. This is never undefined, so we'll set it equal to 0 to find our critical numbers, and we get our critical number to be x equals negative 1. What I'm going to do is just verify that this is in fact a maximum. Just quickly, if we look at a verification of this, if I plug in something like negative 2 to my derivative function, negative 2 in this function is actually going to make that a positive number. Yep. And then if I plug in something like 0, 0 would make that a negative number. Therefore, we know negative 1 has to be the maximum. But that is just the point at which it is a maximum. So let's talk about our max slope and what that is. And we know it occurs when x equals negative 1. So to find my max slope, I'm actually going to go back to the slope equation, which remember was this equation, that first derivative. And I'm going to substitute that in, negative 1. And we get the max slope to be, I believe that's negative 1 as well. So hopefully you did okay with that. All right, the concept that I want to talk about today is linearization. And linearization can actually go by several different names. You may hear it called a tangent line approximation. You may hear it referred to as local linearization. You may even hear it referred to as just a tangent approximating with the tangent line. So really we've got this linearization idea, approximating with the tangent line, and then local linearization are the three main phrases that you could hear in an AP question. So what is it? Well, we can use this line to approximate a value of a function even if we can't actually find the value of the function. And we do that using the tangent line or a tangent line approximation. Okay, so here's what this looks like. If we were to zoom in on this picture, we know that if we were to draw a tangent line at some point P, that if we were to say, let's focus in on just this area, and I'm going to move the screen up just a little bit, and we keep focusing in on this area, and we zoom in just a little bit more and zoom in a little bit more, you'll notice that that tangent line and that curve both appear to be almost the same line. Like we say that at this point P, that at that point, the curve is actually what we call locally linear. Oops, sorry. So if I have a function f of x and it's differentiable at the point x equals p, that x equals p is called our point of tangency, then what we say is that it is locally linear at x equals p. So it's locally linear at x equals p. And what we can do is we can use that tangent line at x equals to p to approximate values that are pretty close to p. So here's how we do this. If we, say, happen to know a very nice point, a nice, what we refer to as a center, we would call, I'm sorry, I'm having a really hard time getting this adjusted to be level. It looks kind of crooked. Anyway, this is a different program than I normally use, so I apologize. But if we're trying to find the equation of a tangent line at a nice point, we would say that the equation of this tangent line would be y minus f of c, so y minus the y value, equals the derivative of the function evaluated at this point and x minus c. Now, the next thing that you probably haven't really talked about before, we're going to talk about something called Taylor's form. Taylor was a mathematician that we are going to use his forms a fair amount, actually. And it's just another way to look at linear equations. Taylor's form really is not much different than point slope form, other than it takes the y value and moves it to the other side of the equation. So we would say y equals the y value, or f of c, times f prime of c times x minus c. So this is what we call Taylor form. And then what we do is we use it to approximate the function at a point A that's really close to C. Okay, so here's what this looks like. The equation that we actually use to approximate is we say that the value of the function at A, some point that is just outside. So if I zoomed into this problem here, this would be like me using P as my center, my nice point, like my C, and then me trying to approximate some point that is just outside. So the line is the linear approximation is very close to the actual curve value. It's just not quite there. But it is going to be a close enough approximation. And so what we say is that the value of the function at A, we'll call this point that we were just looking at A, f of A is approximately the linear approximation at A, which is this f of c, this is that tangent line approximation, and it looks like this. And I'm going to actually be more specific, and let's erase this, and let's put a minus c, because we're trying to find the value at that function. So the next thing that we want to look at is we want to know, and it will be easy to tell, if the linear approximation, that L of A, is actually an over or an under approximation. We do that by looking at the concavity of the function at that point, at that particular point. So if we can find the second derivative, and we know the second derivative is greater than 0, meaning the function f is concave up. If it's concave up, then any tangent line I draw is going to be underneath it, right? So this tangent line, this L of x, will be a under approximation, what we call an under approximation. Or if my second derivative is less than 0, meaning my original function is concave down, then any tangent line that I could draw will be above the curve, and therefore we say that this linear approximation is an over approximation. And that just gives us a good basis to say, hey, I know this is not quite the value, and I know it's a little bit over the actual value, and that's the calculus to prove it. So here we go. Let's look at an example of what this might look like. All right. So the problem says, if f of 2 equals 3 and f prime of 2 equals negative 2, use local linearization to approximate f of 2.01. All this is asking me to do is this is asking me to take and write a linear approximation. Well, what does it require to write a linear approximation or a tangent line? What it takes is a point, which we have right here, and a slope, which we also have right here. And so my function looks like this. My function says L of x equals the y value, 3, plus the slope, -2, times x minus 2. And this is what we refer to as my linear approximation. You could certainly simplify this. I'm going to tell you don't. It's not worth it. Now, here's the deal. This approximation is great at this point because it gives me this slope, and we know we have that line, we have that curve. But the problem is, I don't want to find the value at 2. I want to know what happens at 2.01, something that is relatively close to f of 2, but is not quite there. So we start by saying, okay, let's evaluate the linear approximation at 2.01. And to be honest, most of the time these are non-calculator questions. So we get 2.01 minus 2. And so this value would be 3 minus 2 times 0.01, which means it'd be 3 minus 0.02, which means it would be 2.98. Now here, let me be clear. The linear approximation is 2.98 when we plug in 2.01. That is not the function value. But what we do know is that the function value of 2.01 is approximately the linear approximation of 2.01, which means it is approximately 2.98. This notation is important if this happened to be an FRQ, because this 2.98 is not the value of the function at 2.01. Most likely not the value of the function at 2.01. It is just an approximation. Okay, so let's look at another example. Maybe one more tricky, and if you feel adventurous, you want to hit pause, try the next example, and then come back. Okay, so if 2, -2 happens to be a point on the graph of x squared plus y squared plus 2y equals 4, what I hope you notice, although there is a picture here, what I hope you notice is that this equation right here is the equation of a circle. If we were to complete the square on this, what we would see is that the center of the circle has actually been shifted down, in this case 2 units on the y-axis, but it is centered on the y-axis. So the values on both sides of x are the same, but it is a circle. And it does say use the equation of a tangent line that passes through the point 2, -2. And then it gives me two scenarios: to find a y-coordinate when the x-coordinate is 2.1, and to find a y-coordinate when the x-coordinate is 1.9. So really what we're trying to do is we're saying this point right here is 2, -2. So this is that point, 2, -2. And we want to approximate what happens to the graph when x is 2.1, so something just up here, and 1.9. If we were to zoom in, we would see that that curve actually moves away from the tangent line. It's a circle, it has to. So the first thing I'm going to do, and this work will apply to both of the linear approximations, I'm going to take the derivative. So the derivative with respect to x of this function x squared plus y squared plus 2y equals 4. And certainly you could try to solve for y. I think implicit differentiation would be much easier here. So we would get 2x plus 2y dy dx plus 2 dy dx equals 0. My goal is to find the derivative because I need to write that tangent line approximation, so I need to find a slope. So I'm going to combine my dy dx's. So we would get dy dx is 2y plus 2. And I'm going to subtract the -2x. So let's bring this up here. Dy dx would be -2x over 2y plus 2. And you could certainly simplify that. It might make our life a little bit easier to do -x over y plus 1. And this would be the slope for any point along the curve. But particularly, I want to evaluate this at the ordered pair of 2, -2. So my slope dy dx would be -2 over -2 plus 1 if I use the simplified, which just gives me actually a slope of 2. So my slope is 2. If I write my linear approximation is the y value plus the slope at the point times x minus the x value. And this is my linear approximation. Now, to answer question A and question B, it's really the same two questions. I would say I want to do L of the linear approximation of 2.1, which means it'd be negative 2 plus 2 times 2.1 minus 2. So this would give me negative 2 plus 2 times 0.1, which is going to give me negative 2 plus 0.2, which gives me negative 1.8. And then I would do L of 1.9, the linear approximation at 1.9. So negative 2 plus 2 times 1.9 minus 2. Okay, and so we would get negative 2 minus 0.2. And so my function value at 2.1 is approximately equal to my linear approximation at 2.1, which we said was negative 1.8, or my function value at 1.9 is approximately equal to my linear approximation at 1.9, which was negative 2.2. And that's how we use a linear approximation. Okay. I mean, if you want a really fun party trick, we could also approximate the cube root of 70 by knowing a tangent line approximation. And I'll show you this one because it does seem like it's very far off. We said before we want to choose a point that's near the tangent line, near the nice point, and this one does not happen to be near the nice point. But let's look at it. Or hit pause and try it and see if you can figure out the cube root of 70 without using a calculator. All right. If we look at the cube root of 70, I'm going to use an approximation that happens to be centered at x equals 64. More specifically, I actually need to know what the point is it's centered at. So if x is 64 in the function, the cube root function, my ordered pair would be 64, 4. Okay, now I need to write the linear approximation, meaning I need to write an equation of a tangent line, and I need a slope and a point. So to find the slope, if we start with f of x equals the cube root of x, I guess that said y equals, but this works. I'm going to take the derivative. So I'm going to do f prime of x equals, that would be 1/3 x to the negative 2/3, or it may look prettier. I don't know which one's going to be easier to use, so that would be cube root of x squared. All right. Well, that's the expression for my slope. Let's actually find the slope at 64. And again, remember, my goal is the party trick of being able to do this without a calculator. So this would be the cube root of 64 squared. I don't know 64 squared, so to me it's going to be easier to do the cube root, which I know is 4. So this would be 1/3 times 4 squared, which would give me 1/48 is my slope. So if I were to write a tangent line approximation, I'd start with my y value, we said was 4, plus my slope of 1/48, x minus my x value of 64. Now, if my goal is to solve it at 70, what am I going to do? Well, I'm going to plug in 70. So we get 4 plus 1/48, 70 minus 64, which means I would get 6/48 plus 4. Probably would be easier to reduce that to 1/8, and I know 1/8, and this is all L of 70, the linear approximation at 70. I know 1/8 is 0.125. You may not know that. That's okay. So what we can say is that the function value, the cube root of 70, is approximately equal to the linear approximation at 70, which we got to be 4.125, or 4 1/8. Now, turn to a neighbor and talk to them about how you would explain using calculus. And we have a picture, so we can obviously tell. How could you explain using calculus that 4.125 is not quite right, how would you explain if it was over or under the actual value? So hit pause, try that, and then come back. All right. Well, we can see from the graph, right? We can see from the graph that this at 70, if we're here at 70, let me get 70 up here. Here's 64, here's 70. If we were to zoom in, we would see that the actual value is sitting just a smidge below the tangent line curve. But I don't want to just say that. I don't want to rely on the picture. How can I prove that this is in fact under the curve, an underestimate? I'm sorry, an overestimate where the tangent line is above the actual value? Well, the first thing I would need to do is take the derivative using the first derivative, which we have as, what did I get? 1 over 3 cube root of x squared. And now I need to take the second derivative because I need to show its concavity, the function's concavity. So if we take the second derivative, actually it might be easier to have done this from the 1/3 x to the negative 2/3, because this would give me negative 2/9 x to the negative 5/3. And if I evaluate this at x equals 64, the nice point that we have, the one that we know something about, this would be 64 to the negative 5/3. What I want to know is if this is less than or greater than 0 to show its concavity. Cube root of 64 is 4, and if I raise it to the negative 5th power, it'd be 1 over some big number, 4 to the 5th. But then I'd be multiplying it by negative 2/9. So while I don't actually know what this number is without a calculator, I do know it's going to be less than 0. And so what I would say is my justification, or my explaining with calculus, is since the second derivative of the function is less than 0 when x is 64, then f of x, the function itself, is concave down at x equals 64 and at 70. Therefore, L of 70 is an overestimate. The actual value is less than what we found up above. So the actual value is smaller than 4.125. Plugging it into my calculator, I get that the actual value, the function value at 70, is 4.1212853. So our linear approximation of 70, which we got 4.125, is in fact an overestimate, but by 400ths, or a little bit less than 400ths, which is pretty close. So this is the idea behind linear approximation. Pretty cool application to be able to estimate things when we don't actually have a way to find the derivative at that point, or it can do it without a calculator, so it's pretty nice. So anyway, have a great day, and we will see you soon.